Hello everyone, my name is Axel Lee and I'm a support engineer at Midas IT. As you guys might know, today we'll go to a really basic tutorial on how to model a simple steel composite bridge in Midas Civil NX. The main purpose of today's tutorial is modeling the steel composite bridge manually without using the wizard option that would offer. Furthermore, as you have been aware, the tutorial will be divided into mainly two parts, which the first part will be modeling and the second part will be analysis and design interpretation. In today's tutorial, we'll just go through the modeling aspects, and in the next session, we'll perform the analysis and go through the analysis result interpretations, as well as design capabilities of Midas Civil NX. So this will be basically the outline of the tutorial today. As mentioned before, for today, we'll go through the modeling aspects of the bridge. We'll basically define the properties, which will be the sections and the materials. We'll be doing the geometric modeling of the bridge manually using nodes and elements. And then we'll be applying the different static loads, and lastly apply the moving load conditions. Okay, so for today's tutorial, we'll go through a model, a simple steel composite bridge with a span length of 180 feet and a width of 37 feet. As you can see on the image, this will be basically the cross-section layout of the steel structures for the steel composite bridge for the cross frames. And we will have some intermediate cross frames as well as end cross frames with different steel dimensions, as you can see in the image. So first of all, we will be opening Midas Civil NX. So this will be the main interface of Civil NX. And as you can see, it's quite upgraded. I don't know if you guys have used the previous Civil, but the Civil NX is basically a major upgrade of the UI UX of Midas Civil. And we have created a particular new UI, and for today's tutorial we'll be doing the modeling in this upgraded software. So I already created a new project, and we'll be firstly going to define the material properties. So I'll go back to my slide. So basically first we'll be defining the materials that we'll be using for the modeling process. So first is defining the materials, which will be main material, which will be steel. So as you can see in the presentation, we'll go into the materials remove menu and add the following material. So let's go back to the software, and as mentioned here in properties, on the material properties, once you click that, we'll be getting the dialog box for adding the material properties. Once we click on add, will be pop-up will come up for defining the materials data. So here we'll be firstly selecting the type of design, which will be firstly steel, and for the standard, well, we'll be working with American standards, so we'll be using a ESTM. Also, however, before going and defining the materials, let's first change our units. So as you can see on the right end corner, we have these two buttons. In here, the user can basically change the materials, the units that we'll be working on for the different forces and the length. So because we are using American standards, we'll be using pounds inch, LFB per inch, and the program will automatically take those numbers. Yeah, you can do that also here under projects and on the unit system. If you click that, you can basically change it, the force and length unit systems in here. But if you want to do it a bit faster, you can use the right hand end corner. So once I define the unit system, I can go back to defining my material properties. So once we click on that, we can see that the unit system has been changed. So now I can basically define my materials. So ASTM, and for the steel section we'll be using the DBA36. So once we apply the A36, we can see that for the different section properties, the modulus elasticity, the weight density, etc., has been automatically calculated by the software, and as long as you select the DB, those values will be automatically entered. So then we'll be clicking apply. Okay, so as you can see on the left side corner under the properties dialog box, the material has been successfully added. And a lot of users have questions on why or when to apply OK, or when to click on apply. So for different projects, there are different parts, different materials and different sections you can add. And if you click OK, the properties will be added directly to the system. However, this dialog box will close automatically. However, if you press apply, the section will be directly applied to the dialog box, but this particular dialog box will still be here. So if you need to add different materials, different sections, you can just click apply, and once you define all the materials you need, the last material you'll be assigning, you just have to click OK, and this dialog box will close, and that particular section will be added. So that's the main difference of those two particular buttons. Okay, so I've already added the steel, and then if you go back to our presentation, we'll be also creating some dummy materials for the slab as well as the cross beams. So this dummy material will be basically user defined, and by selecting user defined, the user can automatically add the properties directly. So in here we'll be using, for the dummy material, we'll be using the this particular modulus of elasticity, a Poisson ratio of 0.2, and a thermal coefficient of 5 to the power of -6. Since this is a dummy material, the weight density will be 0. So going back to civil, once I define the steel, I'll go to user defined. And once the user defined is selected, I will go here into the weight density and apply the different the values that we'll be using, which will be 3.8652 e to the 6. So e to the 6 is to the power of 10 to the power of 6. Then as mentioned, Poisson ratio 0.2, and sorry, we have to save our project. We'll do that later. And for the thermal coefficient, we'll be doing 0.5 to the e to the -6. Okay, so once those are applied, I've finished applying all the materials, so I'll be just pressing OK. This is material name. So here we have to define the name of the material, which will be dummy material. Once that is applied, we'll just press OK, and the properties have been added. If we go to our works tree menu, so this is what we call tree menu, which is one of the main positive aspects of civil. In here you can basically see all the applied properties that you have already applied to the software, and in here you can basically see that materials we have defined the steel material as well as the dummy material. So once we define the material properties, we'll move on into defining the section properties. Before going to that, I would just like to mention that if anybody has any questions regarding anything during the presentation or during the tutorial, please feel free to write them down in the comments. We'll be making sure to look into them after the session, and in the next session when we do the analysis and result and design interpretations, we'll have a time to answer all the questions that have been asked, so please feel free to write them down. So we'll be going back into our presentation again. So as you can see, we'll be defining the section properties, and the section properties can be defined under the properties ribbon menu here in section properties, and we'll be first defining the section for the composite section. So in here it's pretty similar to defining the materials. we'll be defining the dimensions for the slab and girders, and also give some material properties. Let's go back to Civil Annex. I'll be clicking onto selection properties, and if I click add, will be directly the section dialog box will pop up, and we have different options for defining different sections for Midas Civil. For today, we'll be using a steel composite, so we'll be clicking on the composites tab, and you'll be directed to this particular menu. So once that, I will be selecting the steel I type 1, and I will name this section pose for section positive, and you can see the image has changed. If I'm not able to see the image, I can just click on the image, and a pop-up will come up with a larger image. If I want to take this out, I'll just click the image again, and it will go back. Next, we'll be defining the different dimensions for the slab. For this slab will be 120 for the width, 8.5 and 2. Then we'll be defining 42, 14, 0.75, 0.4, 4375, 16, 1.25, and then we'll be defining the modulus ratio, steel to concrete, which will be 8, and this TSTC value is the ratio of thermal coefficient of steel and concrete, which we'll be defining as 1. Basically, these ratios basically will be used when the composite section is used without construction stages. I think I didn't mention it before, but in today's tutorial, we'll be doing the modeling without considering the construction stages, so that is why we have to define these ratios. Lastly, we'll be checking on the multiple models of elasticity, and for creep we'll be assigning a value of 24, and lastly we'll be changing the offset to center top. Once it says change that, we can see this red dot, and the offset has been changed to center top. Let's say you guys, if anybody has any questions regarding maybe these different annotations or the values that we see here, what you can do is basically we can look into the manual, the online manual that is available currently online, and you can basically see here what are the different values that we have already inputted for the steel composite. For example, here we select the steel type 1, which is structural steel I-shaped girder, and the different dimensions: BC being the effective slab of the width, PC the thickness of the slab, HT the distance from the top of the girder to the underside slab, and the different materials properties that we defined. For example, here ES over EC is the modulus ratio, TSTC the ratio of thermal expansion. We selected multiple models of elasticity, and this is the criteria that we explained and why that particular point was selected. And yeah, so here using the online manual, anybody can see what are the different functionalities of the different points that we have currently defined. If anybody has time, please feel free to access the online manual, and you'll be able to basically see the definition of each point. We don't want to go into depth on this because it will take a lot of time, so please on your spare time, please feel free to look into those. We'll go back into modeling the modeling process of the section properties. After this, defining the first section, we'll be defining the second section will be our section negative. So once I click apply, we can see that the section has been properly added with the section stiffness scale factor, and I'll be adding another section, right? So I'll be just changing the name, and for this section negative, the the thickness, I think we have a different value for TF1, which is 1.125. The rest is the same, so I'll just click apply, and the second section has been automatically applied. Next, we'll be going into defining the sections for the angles, which will be used for our cross frame. Let's go back to Midas Civil NX. For that, we'll be using this DV user tab. And under DV user tab, because the IDs 1, 2 have already been used, I'll be using ID number 3, which will be the next section. And we'll be selecting angle. In here, I'll be naming my section L4x4x5 over 16, which is basically the dimensions of the angle. And for the DV, I'll be selecting AISC. And once I've selected the different sections for that particular DB will appear. And in here, I'll be just selecting the L4 times 4 times 4 5 over 16. Okay, so once that is selected, as you can see, the different dimensions have been automatically set, and I will be just clicking on apply. The section has been properly added. Then let's go, we'll be adding another section, which will be our W section, sorry, our X section with this particular section name. As you saw in the presentation, we have some end frames or end cross frames, and the top of that particular frame has this particular section, so we'll be defining that section. So going back to Civil NX, we'll be defining an I section, so I'll be changing this to an I section. The section ID has been automatically changed. The name will be using W10X19. And for the section name, since we selected the I sections, the X sections will appear according to the DV. And we will be going down and selecting the W10 by 19. Again, you can see that Civil NX, Midas Civil NX automatically calculates the section properties for this particular section. I'll be clicking apply. Next, we'll be defining the sections for our cross beams and our edge beams, which, as mentioned before, they are used for domain material. So going back into Civil NX, sorry, before that, we'll be using the DV user again and using the solid rectangle option. So in here, we'll be selecting the solid rectangle. The name, so this particular section will be the crossbeam. And since we'll be using no DV, we'll be using user. And once we select user, this particular section is habilitated. And in here, the users can particularly input the values that the user wants. For this particular domain beam, we'll be using 8 by 60. And once that is set, we click apply. And lastly, we'll be creating the section for our edge beam. Edge beam, which will be also a solid rectangle with 0.04 and 0.04 inches of dimensions. Once that is set, we have finished defining all the section data. So I will be clicking on OK. So as you can see, once all these sections are applied, these particular sections are also applied into the tree menu. So here users can particularly check what has been particularly defined in the works tree and what has not been defined. So once we have finished defining our material and section properties, we'll go directly into modeling the steel composite bridge using manual modeling, which will be basically modeling the bridge using node and elements. So let's go back to our PPT presentation, and in here we'll be first be creating the nodes. So under the node and element tabs, we'll be clicking on to create and click on create node. In here we'll be setting up the coordinates for our first node or starting node, and we'll be copying this particular node 36 times in the x direction. So basically here we'll be defining the distance for which this particular node will be copied, and for this we'll be copying it 36 times 5 feet apart from each node. So going back into Midas Civil and X, since we'll be working in feet now, I can go down here and change inches to feet, and let's change this to kips. So we'll be working in kips feet. So we'll be going into our node and element tabs, click on create, and we'll be clicking on create node. Once we click on create node, this particular tree menu will pop up, the same one that we saw in the presentation. We'll define the coordinates for our first node. We'll define how many times this particular node will be copied, and the distance. We said we'll be copying this node 5 feet apart from each other in the x direction. And here we have the x, the y, the z, and this particular node will be copied only in the dx direction. So we're going back here, we'll click apply, and we can see that this particular node has been copied 36 times. I'll click onto ASO view, and if I go into our toolbar, here we have our display node numbers, and we can see that this has been correctly defined. If I want to see particularly the distance between each node, under the node and element tab, I click on query nodes, and by using this, let's go to top view, and I'll be selecting, let's say, node number 1 and node number 2, and we can see here in the command window the different coordinates, and we can particularly see the distance. So we can see that the distance from node 1 to node 2 is 5 feet. So the program has correctly defined the distance between each node. So once we have created this particular nodes, we'll be creating the elements. So let's go back to our presentation, and under the same tab, under create element, we'll be creating our exactly beam elements, and we'll be selecting the element type, which will be our general beam type, and we'll be selecting the materials and sections for that particular element. And once that is selected, we'll go into the node connectivity. We select the first node and the last node, and check on the intersect options, and then click on apply, and the beam element will be automatically created. So going back into Civil and X, I go into create element, or I can just use this particular works menu, go into the elements tab, and in here we can see the different options. For the elements tab, we'll be using create element, select the general beam, the material will be A6, so here we'll be having all the defined materials, and for the section as well, all the defined sections. So for this particular element will be, or beam element, will be selecting the first one, and as mentioned, once this go here, if we go here to the node connectivity, you can see that this particular box has been shown as blue. That means that it's currently habilitated. So if I click here and go back to a model, I just have to click on the first node and push this all the way to our last node. And if I just click on the last node, we can see that our steel composite beam has been created. If I click on this particular option, which is our hidden option, if I just unclick it, we'll be just seeing the line and nodes, or nodes and elements. And if I click hidden, you can see a particular 3D view of the section or the model of the section that has been applied to the beam and to the elements itself. So this is something that we can see basically visually in Civil NX. So let's just for now turn off the hidden option. Let's go back to our presentation, and next will be basically translating this beam element 3 times into the y direction, and each beam or the distance between each beam element will be 10 feet in the y direction. So basically we'll be defining 4 girders in Civil NX. So if we go into this particular option, or we can just go into translate and click translate element, or in here I can just look into the translate element option. The tree menu option has changed, and I'll be, as mentioned before, I'll be inputting a value of 10 feet, and this will be copied 3 times into the y direction. So this particular beam element will be translated or copied 3 times into the y direction. But I have to know the program that I'll be translating this particular element into the y direction, so I will have to select all. So if I click on here, or if I just use the quick buttons, which will be Control Shift A, you can see that the elements have been selected. So once the beams or the line beam elements are placed as red, it means that they have been selected. So once this has been selected, if I just click apply, we can see that the beam or the girders have been automatically applied to the y direction and 10 feet between each element. If I want to see, for example, if they have been correctly displayed, I just click onto hidden, and we can see that the girders have been correctly applied. Now let's go back to our presentation. Next, we'll be modeling we'll be extruding the nodes or copying the nodes into the z direction on a distance of -1.2 feet, -3, and we'll be selecting the first nodes 138.75 and 1.112. This is basically creating the nodes for the cross frames. So going back to our model, I'll be clicking onto our top view. So this is our view cube. In order to select, for example, the top view, the side view, the front view, etc. So I'll be clicking on the top view, and I'll be translating the nodes into the z direction. So I can just click here, translate node, or in here I can just choose translate nodes. In here I'll be selecting unequal distance because I'll be copying this particular node in the z direction on an unequal distance, and I'll be putting -1.2, -3 feet. Then I'll be selecting these 4 nodes. How do I select all these 4 nodes? What I can do is I can do select by window. If I click here, this particular cross will be appear in your model, and if I click and drag, this particular box will appear. So anything that comes into this particular box will be selected, and for this I will just need these 4 nodes. So once I create this box, I will just click again, and I can see that the nodes have been correctly selected. So in here we can also see that the nodes have been correctly selected here. And another option we can use is use this particular select nodes by identifying. And if I click 135, 75, 112 and click on enter, those same nodes will be selected. Once all those nodes are selected, I'll be clicking on apply. And if I go into my ISO view, I can see that the first node was created negative 1.2 feet apart into the Z direction, and the next one was 3 feet, right? So from that particular node, it will be copied 3 feet into the Z direction. Again, if you need to check, for example, the distance between each node and check whether these nodes have been correctly modeled in the distance the user wants, you can always go into query nodes or query elements in order to see the different locations. Now let us go back to our presentation. Okay, so now we'll be basically modeling the cross frame from now on. And for this, we'll be using the create element. So because the nodes have already created, we'll be creating this cross beam element, or the top of our cross beam. So let's go back to Midas Civil next. Going to create element, and again in here we said that we can basically select the section that we already defined. So we'll be selecting our end cross frame section, which will be the W10 by 19, and the material will be the same. Again, the nodal connectivity, we'll be selecting the node that it starts, which will be our node 152, and push it all the way to our node 149. If I just click this, the particular section or the beam element is automatically created. Again, we'll be doing the same for our bottom section for the cross beam. Before that, we'll have to change this to our angle section. Again, click on nodal connectivity. Once that section is habilitated, we click on the nodes below and click on the extrude node. If I habilitate the hidden view, you can see that the top cross frame section has been created, as well as the bottom cross frame has been created. Now we'll be modeling our intermediate cross frames. So as mentioned, we have some end cross frames as well as some intermediate cross frames with different cross frames or different diagonals. So let's go back to our PPT presentation. So we'll be basically translating this the elements 20 feet apart from this particular distance of where the cross frame top and bottom sections have been created, and translated at 20 feet. So let's go back to Civil NX, and we'll be using the translate option, translate elements, and as mentioned, we'll be pushing or creating this element 20 feet into the X direction. Just do it one time, and we have to select the elements, right? So what I can do is I can do select by window, or what I can do is Control Shift S, which will be select single, and I'll be selecting my top and bottom sections of our cross frame. Then if I click on apply, you can see that the intermediate cross frame, or the first intermediate cross frames, will have been created. From here we'll be basically copy the end frames into the particular locations, as well as the intermediate cross frames. We'll be copying them across our bridge. So this will be the next step for our modeling. So let's go back to our presentation. Okay, so before basically copying or translating all these elements across our bridge, we have to divide these elements in order to create some nodes for our diagonal sections, correct? So as you saw in the at the beginning of the presentation, we have some diagonals for our cross frames, but of course we need a particular node in order to create those diagonals, correct? So what we can do is basically divide this element and create those particular nodes. So we'll be doing this. So let's go back to Civil Next, and this particular thing can be done by using the divide option or the divide element feature. And in here I'll be dividing it so divided by 2. So this element will be divided by 2 and a node will be created on that particular place. So the element type, because we are using frames, we'll be using frames, and equal distance basically means this division will be done equally and the node will be created at an equal distance. So as we saw in our presentation, we'll be dividing the top of this element and the bottom of this element. So of course I have to select those elements, so I'll be doing Ctrl Shift S, clicking on the desired elements. Let me just go into a closer look, and if I just click apply, yes, we can see that this element has been divided by 2, basically equal distance between each element, and a particular node has been created. Now going back to our presentation, we'll be basically modeling the cross or the angles across the cross frame. So it will be the same. We'll be going back to Civil Next and click on create elements. So once we are in create elements, we select the section of the diagonals, and again using nodal connectivity, I'll select the nodes, click, and that particular section is automatically created in Civil Next. And I just have to repeat this for the end cross frame. Sorry. Selecting frames. So just click and click, and then we'll be doing it for our intermediate cross frame. So in here, make sure to select the correct nodes. If you select somewhere along the elements, it will basically create a particular node on that particular location. So it's important to make sure that the nodes are correctly selected. So if I just finish this, click Ctrl H or the hidden view, we can basically see that the cross frames have been correctly modeled. Now let's go back to our presentation. So let's say basically we modeled the end cross frame and as well as the intermediate cross frame, but we know that the intermediate cross frame, the intermediate cross frame has a different section, but we just for example, for this particular model, we copied this element into here, and this particular beam element will have the section properties of this particular copied element. But we know that for the intermediate cross frames, this particular section has been used, so we have to change that. So how do we do it in Midas Civil Next? Is basically easy. What we can do is just select the top cross frame for the intermediate cross frame and go into our tree menu and select on the section, and by just clicking and dragging into the model, that particular section will be automatically placed on the beam element. So let me show you that really quickly in Civil NX. So as you can see, the end cross frame as well as the intermediate cross frame has been created with the same section, but we want to change the top of this cross frame, correct? So what, as mentioned, so what I can do is Control S. I'll be selecting my top sections for our cross frame, and I'll be clicking on the section property that I want, click and drop, and we can see that the elements or the beam element section has been automatically changed. So the next step will be basically translating the end cross frames along our bridge, and that can be easily done using the translate element, and we'll be push or copying this end cross frame 90 feet apart 2 times, so it will be basically modeled in the middle as well as the end of our steel composite bridge. So let me show you this in Civil NX. So I have to select the end cross frames. What I will do is basically I don't want all these elements to be selected when I select my end cross frame. So what I basically do is, if I double click on the sections, the girders are selected, and what I can do is I can use the inactivate feature, and the girders will be automatically inactivated. It doesn't mean that they are deleted. And then I want to select all the nodes or the intermediate cross frame that I don't need. So I'll be using the select by window and select all the nodes and elements I don't need, and also inactivate them. So now you can see that only the cross frame has been habilitated, and I'll be translating this. So let's do a front view. I'll be using the translate elements. As mentioned before, I'll be translating these 90 feet into the X direction 2 times. Then I'll select only the end cross frame. Once it's selected, I'll click apply, and you can see that the end cross frame and the intermediate cross frame has been automatically modeled. And if I activate all, you can see the entire model. Now we go back to our presentation. We'll be doing the same for our intermediate cross frames. This will be translated on an unequal distance. We will be creating 7, and each of these intermediate cross frames will be translated 20 feet from each, 20 feet apart. So let's go back to our model. Again, we want to just select the intermediate cross frames, correct? So what I can do is, again, I'll be selecting the top girders, inactivate them, and I'll be inactivating everything that I don't need. Click, deactivate. Then I'll just select all the intermediate cross frames. We'll be doing an unequal distance into the X direction, and it will be 7 at 20. And if I click on apply, you can see that the intermediate cross frames have been automatically modeled. Activate all, and the steel composite superstructure with the intermediate and the end cross frames have been correctly modeled. Now that the structure or the superstructure has been modeled, we have to basically connect the top of the slab with the cross frame so that they can act as a rigid body. So let's go back to our presentation. And yes, so for this we'll be using the rigid link function, and basically we'll be selecting a master node and our slave nodes, and we'll be basically connecting all these nodes rigidly. So we are basically doing this so in order to rigidly connect the slab with the cross frames so that the program can know that the structure acts as a rigid body. As mentioned before, we'll be assigning the master node and then assigning that master node to our slave nodes, which will be, for example, for this case, node 152 and 156. So let's go back to Midas Civil NX. This will be done in boundary tab and on the rigid link option. The true menu will pop up. In here I'll be selecting my master node, which will be 112. This will act as a rigid body. We'll be copying this particular rigid link. Before that, and as mentioned before, we'll be doing this for all the places where the cross frames are located. So we know that they are 4 feet. We'll be creating 4 rigid links at 20, then 2 at 10, and lastly 4 at 20. So I'll just select my slave nodes. I'll do Ctrl Shift S, select node my slave node 152 and 156, and if I click on apply, the rigid link has connected the master node with the slave nodes, and it has been done for the complete model for the left side. So we have to do it for these intermediate places as well as the right hand side. So I'll just go zoom in here really quickly. Just change the master node. For this case it will be 75. And again, select single, select the slave nodes, 151, 155. Make sure they are selected. Click on apply. Again, for this node, it will be master node 38. Select 150. Sorry. It's no 150, 154. Click on apply. And lastly, this master node 1. Select single, 149 and 154. If I click apply, we can see that the rigid links have been correctly applied to my entire structure. So now we'll be creating our nodes for our support conditions. So before that, let's just display our rigid links. In the tree menu, I just have to right click and click on display. Going back into our presentation. So we basically copy the nodes of our bottom cross frame and translate them 1 feet into the Z direction. Going to Civil NX. I'll go into nodes. I'll translate nodes, and it will be on equal distance, 1 feet apart. And I'll be selecting the nodes which were 153 to 154, 177 to 180, 188 to 191. If I click enter, I can see that the nodes have been selected, and if I click on apply, the nodes for the support conditions have been correctly applied. So going back to our presentation, we'll be basically creating our elastic links in order to connect the nodes for our cross frame with the support node with a defined stiffness set by us, our user, and this will be the values for the different stiffness for that particular elastic link. We will be also copying this particular link to the distances where the support conditions are. So let's go back to our model. This can be done in the boundary condition tab under elastic link. And in here I'll be setting up the values, which will be 10, 1 e to the 10. I think they have been already applied. 10 for the rest values. I'll be copying this particular elastic link where the support conditions are, and I'll just have to select these two nodes. Select and select, and the elastic link has been created at the support conditions. We'll be doing this for the other support locations. So for the two nodes, I'll just have to simply select this node, this node. Again, the same for this nodes, and lastly for the end nodes. So if I click on the answer view, we can see the elastic links have been successfully applied. So now we want to display the elastic links. Well, what I can do is just click on to initial view, and we'll have a clean view of the model itself. Let's go back to our presentation, and we'll be defining the support conditions and fixing them all to create fixed conditions for supports. This can be done in the boundaries tab under define supports. So going back to Midas Civil boundary define supports, we'll be basically defining, restraining all the directions, rotation and displacement, and I have to select the nodes, correct? So what I can do is I can do select by window and select the nodes for the supports. Once they are correctly applied, I just click apply, and we can see that the support conditions have been correctly applied to the model. Now once the support conditions are modeled, let's go back to our presentation, and we'll be basically modeling the cross beam and edge beam. So for this, we'll be basically using the same translate node options, and we'll be basically activating only the girders in order to facilitate the modeling of the cross beams and edge beams. So first we'll be creating the nodes for our edge beams. So let's go back to Civil NX. As mentioned, I'll just want to select my girders, so I'll just double click on my section for my girders and click on activate. Once those are activated, I'll just close my hidden view, put on the top view, and I'll go into nodes, and I'll be translating the nodes, correct? Okay, so I'll be translating these nodes at an equal distance. They will be 3.5 feet apart. We'll be doing first the left side, leftmost, this part first. I will select all the nodes. Again, I'll do the select by window, select all my nodes on the left side, and click on apply. All the nodes have been created, and I have to do the same for the leftmost side. I'll just change this value to positive 3.5. Again, select all the nodes that have to be translated, and click apply. Here, so now we have created the nodes for our edge beams. So once the nodes for our edge beams have been modeled, now let's go back to our presentation, and we'll be basically modeling our cross beams. We'll be firstly create the first cross beam and basically translate this beam element across our superstructure. So first I'll going to create elements. I'll select my dummy material as well as the section for my cross beam. For nodal connectivity, I'll click on the first node 282 and click on the outermost 319, and the cross beam has been automatically created. Then as mentioned, I'll be translating this particular element across my bridge. So I'll just go back to translate elements. I'll be copying this element on an equal distance, 5 feet apart in the x direction, and 36 times. For that, I have to select the element itself. So I'll just select my crossbeam elements and click on apply. Now we can see that the crossbeams have been automatically modeled in Civil NX. To see, let's just open the hidden view and activate all. Yes, so the slab or the dummy section for our crossbeams have been correctly applied. Now let's go back to our presentation, and the last step will be basically modeling the H-beams. So we'll be creating these particular H-beams on the locations where the H-beams were. It's pretty easy. Just go back to Civil NX, create elements, and I'll just turn off the hidden view. Go into my top view. I'll select my section name, the H-beam. Nodal connectivity, connect the nodes for my H-beam. That's created, and lastly, this. Okay, so basically my grillage model has been basically modeled in Civil NX with lines and elements. Once the manual modeling of the superstructure with bender coordination is completed, we'll now move to defining the static load cases as well as the moving load cases. If we go back to our presentation, we'll be having different static loads, including the self-weight of the superstructure itself, some loads for the crash barrier loads, as well as dead loads for rolling surfaces and utilities. These static load cases can be easily defined in Midas Civil NX. Under loads ribbon menu, under static loads, we have a static loads case. In order to go on with the presentation a bit fast, I already defined the different static load cases, so we will directly move into applying the loads for the different static load cases. So as you can see in the presentation, we will be first adding the self-weight. The Midas Civil will automatically calculate the self-weight of the superstructure considering the materials and section properties, and the only thing the user has to do is define the direction of the self-weight. Then we'll be creating or applying some beam loads for the static loads for the DC2 loads as well as the DW load. This will also be in the global Z direction and will be applied to all the girders. And lastly, we'll be applying some loads for the crash barrier, which will have a value of this, and this will be applied to the H-beams. So let's go back to Midas Civil NX. So under the ribbon menu we have our self-weight, and in here we'll be selecting the load case for our self-weight, which will be DC1. And in here, as mentioned, we just have to apply the direction of the load and click on add. Once that is applied, we can see on the tree menu that the self-weight has been applied, and the program will automatically calculate the self-weight of the structure. Then we'll go to the beam loads for the different crash barrier loads as well as dead weighing surface loads. And under beam loads, first we'll be applying the loads for the DC2 loads. It will be a uniform load on the global Z direction, and we'll have a value of negative 0.26 kips per feet. Now we have to select all our girders. What we can do is just select the section where the girders are and hit apply. Once I apply, we can see that the uniform loads have been correctly applied. Then we'll be applying the dead wearing surface loads, and this will have a value of negative 0.213. Again, we have to select all our girders, double click on the section and click on apply. So once we have finished defining our static load cases, we'll be moving on to defining our moving load conditions. So going back to the presentation, before that we have to first define our dummy beam groups. So under the group tree menu, we can basically define different groups for our structures and assign the different sections, or let's say beams, girders, etc., to different structure types. We'll be doing this, I'll show you in the model itself. So under the tree menu, under the group tab, I'll be creating a new group which we will call dummy beams. And as you can see in the works tree, no zero nodes and zero elements have been assigned to this particular structure group. So what we have to do is we'll be selecting all our dummy materials, and the dummy materials will be automatically selected. And just as we did with our section, we'll be just clicking our structure group and click and dragging it to our model. Then we can see that all the elements that are particularly for the dummy beam have been assigned to this particular structure group. And if I just double click on this, all the dummy beams will be selected. Now that the dummy beam has been selected or applied or defined, we'll go into our moving load conditions. So under the moving loads, the first thing you have to do is select the moving load code. For today we'll be using S2RFD. And as you can see in the presentation, we have basically defined the moving load code, and we'll be firstly defining the traffic lanes. So the traffic lanes will be defined considering an eccentricity. We'll be defining a particular lane and provide an eccentricity for the program to know at what distance this particular lane will be applied. For today's tutorial, we'll be defining exactly 3 different lanes, and after defining the lanes, we'll be defining our vehicles and then move to defining our moving load cases. So going back into our model, I'll go into the traffic lanes and I'll click on add, and this particular dialog box will pop up. I'll change my view to top view, and I'll first name my lane 1, which will be considered the first lane, and give it an eccentricity of 8.5 feet. Then under this option, on the vehicular distribution, I'll be selecting my cross beams. Under the structure cross beam group, I'll be selecting my dummy beams. When using the crossbeam type option for the vehicular distribution, the eccentricity is used only for locating the lanes from the lane element. The vehicle loads are distributed to the girders by crossbeam elements defined as in the crossbeam group. If the user is modeling a bridge with multiple girders, such as the ones we have, this type of vehicular distribution is basically recommended. Then for example, defining all this moving load conditions is pretty complicated, and if it requires a little bit more time, so maybe in a further session we'll be describing all our moving loads functionalities and features, but for today we'll just explain the very basics. So then after selecting our dummy beams for our crossbeam group, we'll go into selection by, and we'll be doing the selection by 2 points. In the first row, we'll be selecting our first node for the particular lane and push it all the way to the last node. And once I click on that, the lane has been defined with this particular eccentricity. If I click OK, I can see that this lane has been applied. So what's the eccentricity? So I made this particular beam the reference line, and I gave it an eccentricity of 8.5 so that the program can know that the first lane will be 8.5 feet apart from the reference line. So let's just add the next two lanes really quickly. Lane 2, which will have an eccentricity of 18.5 feet. The same will be selecting the cross beam groups, dummy beams. Again, since this is just eccentricity, I can just select the same element and check that the eccentricity has been correctly applied, and just click apply. We can check all that here on the traffic light lanes. As you can see, the second lane has been correctly applied. And lastly, we'll define our last lane, lane number 3, which will have an eccentricity of 28.5 feet. Before that, we have to delete all this definition so that the program knows that we are defining a new lane. Just here I have to click on delete, go to this selection, and do the same as we did for lane 1 and lane 2. And we can see that the last lane has been successfully applied with this particular eccentricity. I'll be clicking OK, and we can see that our 3 lanes have been successfully applied to the model. Now going back to our presentation, we'll be defining, as mentioned before, our vehicles. So Midas Civil NX basically, once you select the standard or the moving load code, the program has the different DVs for the different vehicles that are stated on the design code. So under here we have the HL93 truck vehicle, which is the load or the vehicle load that is defined in the Astro RFD. And for today's example, we'll just be defining this particular vehicle load. And as we know, in Astro we have a dynamic allowance of 33%. So I will just be clicking OK and defining just one vehicle for our moving loads. Lastly, we'll be basically, let's say, combining the traffic lanes with the vehicles in order to create our moving load conditions. Moving load cases. And that load case particular will be called MBL1, and this particular vehicle will be loaded, minimum loads, the loaded lanes will be 1 and the maximum loaded lanes will be 3 lanes. So if we go back to our model, under the same tab, we'll be clicking on moving load cases. Click on add. And we'll be calling our moving load case MBL1. MBL1. And we have to add the vehicle classes as well as where this vehicle will be placed, right? So as mentioned before, we'll be doing minimum loaded lanes will be 3 lanes and the maximum loaded lanes will be 3. I'll be selecting all my lanes that I define for my traffic lanes and push it into the selected lanes. Once I click OK, the vehicle class has been defined for these 3 lanes, and I'll just have to click OK in order to create my moving load case. And lastly, for today's presentation, we have the moving load analysis option. So in this, we'll be basically controlling the data that we'll want for the analysis results. If the user wants to output the concurrent forces for the max and min values required for the movement loss analysis, you'll be selecting the normal plus the concurrent forces so that Midas Civil NX can basically calculate all those concurrent forces and stresses and give you the result values for those. And basically one can apply filters to obtain certain specific results and groups only. So this is basically what it's explaining. We can, if we don't need, for example, the reactions or let's say displacements, and I just want to see, for example, the forces and moments for the calculations, I can just basically select those options in order to let the program know that these particular calculations can be skipped for the analysis. So this particularly analysis control data can be used basically for in order to speed up the analysis process, and a lot of engineers use it in order to just, let's say, if they have a very heavy model, they'll be just selecting the forces that or moments that they need, and basically doing that, the program will automatically know and just output the required analysis results. So thank you very much for today. As mentioned before, if anybody has any questions regarding today's tutorial, please feel free to mention them in the comment sections, or the place where you can write any comments. As mentioned before, this is just part 1, which will basically we saw about the modeling process of the steel composite bridge. And on the next part, which will be part 2, we'll be running the analysis and looking at the different results, how to look into the different results in Midas Civil NX, what are the capabilities. Then we'll go into design and see the different design capabilities for steel composite bridges in Midas Civil NX. As well as I mentioned before, the questions that have been the questions that you wrote in the comment sections, we'll be looking into those also. And in the next session will be, before going into the second part of the presentation, we'll go over all the questions and answer them as thoroughly as possible. So thank you very much for your time, and hope to see you in the next session. Thank you very much.